All right, hello and welcome everyone to our pre-class video for the second day of 14.7. Here we're going to be talking about absolute mins and maxes. And so in order to do this, we're going to start off with a theorem called the extreme value theorem. Now, my claim is that we've had the extreme value theorem before back in our Calculus 1 days. However, back in Calculus 1, we needed that, again, f to be a nice continuous function on a closed and bounded set. And basically what closed and bounded looks like in Calculus 1 just means that you need a closed interval not going off to infinity. So for instance, something like 1 to 3 would work perfectly fine, or 5 to even 1001, or things like this, right? So long as it was closed, right, those brackets means that it includes the endpoints and that it doesn't go off to infinity, bounded, then we're good, right? And the claim is that the function will achieve its maximum and its minimum at least once on that set then. Now, here in Calculus 3, closed and bounded is a little bit more complicated. And so I need to tell you what closed and bounded really means in a plane, right? So this is the R2, our real plane here. And so, and maybe to start it off, I want to jump here really quick down to part C. Maybe I should have done this in another order here. But let's start with a bounded set. I want to skip closed for just a quick second. A bounded set just means that it doesn't go off to infinity. Of course, going off to infinity, when you're talking about the real plane, right, there are many ways that you could go off to infinity. And so basically what this comes down to is that you can trap it within some disk. Disk just means a circle plus its insides. So whatever D is, so long as D is not something like the first quadrant, right? The first quadrant, there's no way you can trap the first quadrant within a disk of any finite radius. And so your set couldn't be like the first quadrant or the second quadrant or things like this. But so long as D is some region here, right, that can be trapped within a disk. So here's maybe our region D. And we can see that certainly I can trap this within some disk of finite radius, right? So long as I can trap this within some disk, right, that it's contained within some disk, right? It doesn't matter what the center is. It doesn't matter what the radius is, so long as it's a finite radius, right? Then it's a bounded set. So that's the equivalent of saying it's bounded here in two variables, x's and y's right here in the xy plane. Okay, now we need to talk about closed. Now, closed in the Calculus 1 just means that it included its boundary points. It included its endpoints. So I need to tell you what a boundary point is. And we'll look at this one here in just a second. But once we know what a boundary point is, a closed set is going to be one that contains all of its boundary points. So let me first give you kind of the intuitive definition here. So the boundary points are, of course, those points that are on the boundary. Now, usually, if it includes that line, right, we usually mark it with a solid line like I have here. If it doesn't include that line, right, then we would go ahead and maybe do a dashed line. So I could go through with a dashed. And if I did this, right, it goes all the way up to this boundary line, but then it doesn't include it, right? This would be actually called an open set. And so a closed set is one that contains all of its boundary points. So we would usually denote that with a solid line. All right, so that's intuitively what this is trying to describe to us. Now let's look at the formal math definition here. A boundary point of D is a point such that every disk with that center contains points both in D and not in D. So this is kind of, it's maybe surprising that this is like the simplest definition, but disks are relatively nice things to describe even with equations in math. And so a boundary point, so let's first of all, let's take some here. I hope we agree that this is not a boundary point of D. And notice what happens is that you can find some disk with some radius centered at that point, right? And that's not to say that every disk, just that there is at least one disk where this disk here doesn't have points in it that are both in and out of D, right? All of these points are out of D, right? So this is not a boundary point. Likewise, you can even choose one that's quite close to the edge there, but so long as it's not actually on the edge, right? Again, you could choose a smaller radius here, right? And those points there are entirely within D. So it does not contain, right? This disk here that I've chosen shows that not every single disk has points in D and out of D, right? So of course, if we choose one that is on the boundary, maybe over here or something like this, then no matter how small you choose that radius for your disk, right, still you're going to have some points that are in D, shaded green, and some points that are not in D, right? In this case, not shaded whatsoever. And so that's what a boundary point is in the two-dimensional sense. And again, if we include all of the boundary points, right, then that's what it means to be a closed set. So if a set contains all of its boundary points, then it is a closed set. Even if it's missing a couple of them, right, it's not technically a closed set. In fact, many sets out there are neither open nor closed. It's not kind of an either or sort of deal. There are open sets, there are closed sets, and there are sets that are neither open nor closed. And if you want some additional reading, there's actually two sets that are both open and closed. So there's a little bit of bonus for you. Go and find what sets those are. They make your head hurt a little bit, but once you really get a hold of those definitions, technically it's true. All right, so I need to tell you about these, right? Now we understand what closed and bounded sets are, so when we can actually play this game. And now from the extreme value theorem, we can see when we know a function will actually achieve its maximum and minimum, right, on which sets those are and all that sort of stuff. The problem with the extreme value theorem is that it doesn't help you whatsoever in actually finding where those minimums and maximums are. It just says they exist, but it hasn't told you, where do I look for these things, right? And so this theorem here is a strategy, right? How will you actually go about once you know that a minimum and a maximum exists, right? Once you have a continuous function and a closed and bounded set, extreme value theorem, right? How do you go about actually searching for minimums and maximums? And so this is the strategy here. First off, I think that we should try to find all of the critical points within D. So find the values of f at the critical points inside of D. So this is all of the stuff that we did in our last class, 14.7a, right? We found critical points, right? And we classified those critical points. The next thing is that I'm going to try to find critical values of f on the boundary of D. And we're going to try to collect all of these things on a list. And then the largest of the values from steps 1 and 2, claim is that list there will be comprehensive. And so the largest of the values from those from steps 1 and 2 will be the absolute maximum. And the smallest is going to be the absolute minimum. Let's kind of do a quick review here, how we did this back in our Calculus 1 days. Again, kind of this will help us transition into the Calculus 3 stuff. So in Calculus 1, you may have had something like this, right? Let's suppose we were looking for minimums and maximums on the interval from 1 to 6 or something like this. And a nice closed and bounded set, right? Doesn't go off to infinity here. We're on the set from 1 to 6, and we do include the endpoints. So no open dots or anything like that. So in our Calculus 1 days, we would find our critical points, right? So here and here are critical points. But then remember, you also need to include in the endpoints, right? So we'll have our endpoints. And these could also be mins and maxes, right? And so we'll be doing the same thing, in particular when you get down to searching the boundary, which is in its heart, right, kind of a one variable, one-dimensional thing, right? You will also need to include in the endpoints. And so we'll be looking for the critical points, right? And those values, but also you need to include in those endpoints as well. Okay, well, with that, let's go ahead and try this out on a problem. So I would like to find the absolute maximum and minimum values for this relatively straightforward function starting off here on the region D given by the picture below. So this is, it looks like the region inside of a parabola capped off by the line y equals 3. And the parabola is y equals x squared minus 1, seems to be kind of this lower boundary here. So the first thing, according to step 1, is that I would like to try to find critical values or critical points, just like we did in 14.7 part A, or the first part there. So I'm going to take partial derivatives with respect to x and with respect to y, and I'm going to try to figure out when are these 0, right? When are they both 0? So if I take my partial derivative with respect to x, okay, here's my function over here. Partial derivative with respect to x is 1. Partial derivative with respect to y is also 1. And my question is, how can I make both of these equal to 0? What values of x or y could I plug in where they're both equal to 0? And the answer is, well, sadly, there aren't any ways to make these both equal to 0. They're constants, right? They're both equal to 1. And so there are no critical points that we get from this first step. And sometimes that happens, right? Sometimes there aren't going to be critical points from step 1. And that's perfectly fine. So now we can move on to step 2, right? Again, there was no ways, no matter what values you plugged in for x or for y, right, that we ended up getting 0 for our critical points. So now we need to go on and look at the boundary, right? So step 2 is looking at the boundary of D and finding those critical values on the boundary. Now, the interesting thing here is that my boundary is actually made up of 2 pieces. So if I'm looking at just kind of graphically here, my boundary for this closed and bounded region D is made up of this line, y equals 3. Oops, did a bad job there, y equals 3. And then it's also made up of this parabola. Those are my 2 boundary pieces. And so I will need to search both of those boundary pieces and see what kind of critical values we get from our function on both of those pieces. Let's go ahead and start off with this easier one first. This is y is equal to 3. Notice that this is not the entire line y equals 3 though, right? It doesn't go on forever. It seems to stop where these 2 curves meet. So maybe my first thing is trying to figure out what is the domain of this, right? Where am I actually looking on this line y equals 3? And so if I set these things equal to one another, right? 3 is equal to x squared minus 1. We can rearrange and get x squared is equal to 4. And so x should be equal to plus or minus 2. So these things meet at -2 and at +2. Okay, so again, I'm not really looking on the entire line y equals 3. I'm just looking between x ranges from -2 to 2. So this tells me already actually about some endpoints, right? Remember, when we're on kind of this one-dimensional item, this line here, we're going to need to look at our endpoints, but also our critical points. So our endpoints that we need to add to this list are going to be -2, 3, and 2, 3, right? And we can actually just use this picture here to maybe start collecting all of these as well. These right here are the endpoints for this line segment. We also need to search within the line segment. And again, we're looking for critical points. We're looking for critical points for our function here, but with this specific value for y in this case, y equals 3. So if I was to go ahead and do now, instead of f of xy, right, which would be the full notation here, which x plus y. Here, I'm only searching on the line when y is equal to 3. So I'm going to swap in, instead of y here, I'm going to go ahead and plug in 3. So instead of y, plug in 3. So this right here is my single variable function. And again, now we're back in calculus 1 world, right? I'm trying to find the maximums and minimums, in this case, just the critical points, because this is where all the potential mins and maxes will be for this function, x plus 3. So we can take the derivative of it. And remember, just like we're doing here with our critical points, right? Back in calculus 1, critical points were found when the derivative was either undefined or 0. Again, sadly, no way that we can make this undefined or 0. So there aren't any additional points. right? But then we also need to include in those endpoints, because again, those endpoints where x ranges from -2 to 2 could be mins and maxes. And so right now we do have the -2, 3 and the 2, 3 that need to be added to the list. All right, this one may have been even like too simple. It may be confusing because it's too simple, right? We're just not getting critical points, right? When we take the derivative, we can't make it equal to 0. I promise you here in this next one, we will be able to find some critical points. So again, we are not looking at the entire parabola though, right? The entire parabola would keep on going forever and ever and ever, right? We're only interested when x ranges from -2 to 2. And so we know that plugging these things in to now our parabola function, if I plugged in -2, square it, subtract 1, I would get -2, 3. And if I plugged in +2, we would get 3. And those are the same points that we already have. So those are already on our list. We don't need to double add them to the list or anything like that. And so I'll just kind of forget about those for right now. And now let's go and search for critical points. So again, critical points, we're looking at our f of x, y, which again was x plus y. But now, right, we are only searching on this point where y is equal to x squared minus 1. So instead of y here, let me go ahead and plug in x squared minus 1. X squared minus 1. And so this will be my function. Again, just a nice single variable function. Let me go ahead and maybe rearrange this a little bit. Usually I write my polynomials with a higher power first. So now we are back in calculus 1 days. Again, I'm trying to find mins and maxes for this function here. So I can take the derivative, 2x plus 1. I can ask, when is that derivative undefined, or when is it equal to 0? Well, it's never going to be undefined because I don't have any square roots. I don't have any division. I don't have anything like that. However, it is equal to 0. Let's see, when 2x is equal to -1, or that is when x is equal to -1/2. So when x is equal to -1/2, we actually have that the derivative is equal to 0 there, and this could be a critical point. So that's going to be somewhere maybe around in here or so. That's when x is equal to -1/2. But let's get the full point, right? So if I wanted the y value here, I would go ahead and I would plug that in to my y equation, and that'll give me y is equal to -1/2 squared minus 1. So that's going to be 1/4 minus 1. So that's going to be -3/4. So we have this point here of -1/2 comma -3/4. And since I did the other ones in blue, why don't I go ahead and do this one in blue as well? So now we have collected, right? We've looked at all of the boundaries and we found the critical values there, including the endpoints, right? We searched very quickly. Sadly, there wasn't any critical points in this case, but we now have a comprehensive list from steps 1 and 2 here of all the places where a possible min or max could occur. And so for step 3, we are going to plug these things into our function, right? So -2, 3, +2, 3, and -1/2, -3/4. And again, remember our function is the summing function. We're just adding to those coordinates together, x plus y. So let's go ahead and plug these things in. So -2 plus 3 is going to be 1. 2 plus 3 is going to be 5. -1/2 plus -3/4, -5/4. The smallest of these values here will be the absolute minimum. In this case, -5/4 is the absolute minimum. And the largest of these will be the absolute maximum. You'll see also in web work, it'll ask for these values, right? What is the absolute minimum? What is the absolute maximum? But they may also ask, where do they occur, right? And so in this case, the absolute maximum occurs at the point 2, 3, and the absolute minimum occurs at the point -1/2, -3/4. All right. I know this is a lot of information to take in about critical points and searching boundaries. excuse me, and all that sort of stuff. Luckily, we will get the entire class period to kind of do more of these types of problems and learn more about this. So there's definitely more coming. I'm not expecting everyone to be at 100% just from this one short example here. So, all right. Thank you so much, everyone, and I'll see you in class.